All right, this video is going to be on Unit 4, Energy and Work. So what is work done? Work done is given by definition, it is a force acting on an object and displaces it and changes energy. So the formula that we normally use when you have a constant force is going to be FD cosine theta, and it is going to be considered positive work when your force and displacement are parallel and the theta is 0, which means in the same direction. And it's negative if your F and D are parallel but your theta is 180. Just in case of friction, your work done is going to be negative, and the work done is 0 when you have your force and D are perpendicular, such in case like work done by gravity or force normal. So that's the case where you will have 0 work done. So there are work done by conservative forces. Conservative forces are your force of gravity and spring force. Keep in mind spring force is negative kx, and the work done here is going to be given by change in potential energy. Just keep in mind conservative forces work done is change in potential energy given by negative U final minus U initial, or when you distribute it, it's going to be U initial minus U final. Remember, these are path independent, which means the work done is going to be the same no matter whether you're going to take this, push this block by a force to a ramp of the same height, and then the same with this, with the same thing. So it is path independent, so it has to be same work done. Let's say in the scenarios like where you have non-constant force, if you see it's the forces are non-constant, it's like raising and staying and then going down. If you give an FD curve, the area under the curve is going to be your work done, and it is also equal to change in kinetic energy. Remember, if your work done is under the axis, consider it negative and you will do the net work. Okay, this is a good example of a work energy theorem. So where we are given an object at rest, and then it is going through the ramp and a flat surface, and we are given a final velocity v on that, and we are not given this distance. They're asking you to find the distance it would travel here, and this d1 is also not given, but we can find it. Mass is also not given. When you have a problems in physics, usually like when mass is not given, they eventually cancel up the terms. So here, so first the thing is, work energy theorem states that change in kinetic is equal to total work done. So we need to consider into effect all forces that would contribute to work done for each ramp and the flat surface, and sum equate to change in kinetic. Change in kinetic is 1/2 mv final square minus 1/2 mv initial square. Since we started at rest, that is going to be 0. So we can calculate this, like equate it to that. And work done. Work done on the ramp is going to be like, we have if you do the free body diagram, I have force normal and I have force gravity and I have frictional force. These three are the forces that could contribute to work done. You know that work done by normal is going to be 0 because theta is 90 degrees on that. And it's also perpendicular force, right? And if you would divide your WG, we have two components, mg cosine theta and mg sine theta. Mg sine theta is going to be my parallel component to the direction of motion, so it will contribute to work done. And then the d1 is not given, but you could use like trig by doing sine theta equals opposite over hypotenuse, which is your t1, and get it here. And then work done by gravity, we only have the horizontal part that's contributing to the work done. By friction is going to be mu1 times force normal times d1, sorry. And you also know force normal is equal to mg cosine theta, so we plug that in. And for the flat surface, we only have two forces, Fg and N, and friction, 3 forces. But there will not be any gravity component that will be parallel to the block. So we will have both these components 0, and we only will have work done by friction. We're going to do that as mu2 force normal times d, and then you equate all these to final kinetic energy. Like we said, that is your change in kinetic. And remember, if you see it, masses all cancel out, and then you're going to solve for unknown d. This is basically explaining how we are setting up total work done that is contributed by different forces, and keep in mind the directions of the force and the displacement, whether you get a positive or a negative. In this case, when you do the friction, when you plug it in, this term actually will become negative because of the cosine. The theta is going to be 180, and then also the frictions work done is all going to be negative on that. So keep that in mind when you do it, and you solve for D. Thank you.
Just a little clarification on the last part I spoke about. So the negative comes for fraction no matter what this theta is, because it's like always a negative work done. But on a ramp problem, you will have a theta component that's contributing from the force normal, whereas here you don't have a theta. For this theta, you still would use the ramp angle, but this negative comes from definition of work done. Hope this helps. Thank you.
Alright, this is going to be the conservation of energy for a vertical spring problem. So let's say we start off with a spring with its initial length is L0, and we add a mass to it, and it's stretching to an equilibrium position. Let's say it's stretched about 25 centimeters. So and then we are pulling out with another stretch of 11 centimeters, and then the question is asking you how far up it can go back. So we use the conservation of energy. So we are going to be like, initial energy would be equal to final energy, sum of them. So initially we have spring potential energy, and since it is being given a velocity and pull, we are having a kinetic energy. And finally, we'll have a spring potential, and we will not have a kinetic energy there, because remember, at the extreme positions in the springs and pendulums, you know that kinetic energy is 0 at the maximum height. So spring potential is given by half kx square, where a is the a distance that we have stretched, and then 1/2 mv0 square, and then 1/2 k, the final y position that we are going to solve. And we could use your mg equals kx, the Hooke's law, to find the spring constant if your spring constant is not given, because we're given a stretch. And then we can plug that here, and we are given the stretch of 11 centimeters here, and then we are also given initial velocity. So if you plug everything in, you get your y final to be 32 centimeters. If you look at this, visualize it, that's at equilibrium, and then which means it could go up to 32 and negative 32 on that side. So since we're talking about the maximum value it could go, we know that it is going to a maximum of 32 centimeters. And if they ask you how much it's being stretched from its original, we know that originally it was at 25 centimeters when the block was added, which means it would go further like 7 centimeters above its original stretch. Hope this helps. Thank you.